Welcome to Convection Part 2A. So this is covering Bergman section 6.4. So today our learning objectives are to develop relationships for the boundary layer analysis. So within that boundary layer that we learned about last time, how do we analyze the flow, how do we analyze the temperature? We're going to relate the thermal or energy equations to velocity and mass. So we'll look at how we apply conservation of mass, conservation of momentum, and conservation of energy to a control volume. And then we'll talk a little bit about compressible and incompressible flow and how those are related. So we start here with a differential element. We're looking inside of our boundary, right? So we're down in this region. We can see that we have a thermal boundary layer, delta T, that goes all the way up to this top dashed line. And our first dashed line, if we look over here, here's our velocity boundary layer. Delta is just this section right here, and the other one, delta T, is this whole section. And if we look at our plot of U, we see that that ends and is fairly vertical, and it appears that our coordinate system is rotating along with our perpendicular to our flow here, so our Y is always perpendicular to our surface. And when we look at T, our delta T is looking like it's pretty vertical here, maybe not quite at that point, but anyway, our differential element is inside of our boundary layer. Inside of that, we're going to look at what's happening. We're carrying mass in with X and Y components of our flow. So we have mass entering and leaving with X and Y components of velocity. We have energy entering and leaving. Some is coming from our velocity, our kinetic energy, and some is coming from thermal energy or heat transfer. So there's going to be some temperature going on. We're going to have some heat transfer as well. So we've got this Q double prime S, so we've got some heat flux coming out of the surface, and we're seeing how that energy enters and leaves the system. So what do we have? We're going to assume that we have laminar fluid behavior. Why are we doing that? It's a little more simple. It has pretty constant velocity. It's not going to be varying with time or with any other disturbances, as we discussed before in the transition and turbulent regions. What's our goal? We're going to try to get to some differential equations. So I know, kind of scary, right? Diffie Q. We're going to model our velocity and temperature fields using some Diffie Q. We're going to assume that we're going to have 2D flow, so it also apply in 3D, but we're going to start with the simpler case of 2D flow. We're going to assume incompressible fluid. Compressibility is something we'll talk about briefly at the end here, but basically we're assuming our density is constant or only varies with temperature. We're going to have constant properties, so mu, rho, nu, etc. are all going to be constant with respect to each other. Well, not to each other, but to a given value. And then we're not going to have much body forces going on. So we do have some gravity, but it's not going to be very significant in this case. Or we don't have any magnetic field. We don't have like magnetic particle, like iron particles in our field or flow that's going to be impacted by some magnetic field or something crazy like that. And we're not going to generate any temperature energy through a chemical reaction or other way of generating thermal energy. So what do we have going on? We're going to start with just considering about this, right? So we had our boundary layer. Oh, say we have kind of a plate. As we get that flow coming over it, we're going to have this growing like this. So we're going to have velocity that's going here, coming up, similar to what we saw in our last videos, right? So as we look at that, as we go in the X direction, what do we see? We see that our flow-wise in the X direction changes much less than our flow in the Y direction, right? As we go up, we're going to see bigger gradients in the left-right velocity than we do as we go left and right in the left-right velocity. Similarly, our temperature gradients are going to be responding in the similar way. As we go in the left-right direction, the X direction, the second of temperature with respect to that X direction is going to be much less than what we see as we go up and down. And that makes sense, right? Our velocity boundary layer and our thermal boundary layer are both predominantly in the up and down direction. Those lines defining them are largely horizontal. So what does that mean? What can we do when we see that these changes are more in the y direction than the x direction. Well, we're going to throw out the smaller x variations. They still exist, but they're not going to be as important in developing this. We find that inside the boundary layer, the pressure gradient inside that boundary layer is the same as what we get outside the boundary layer. We're in that free stream. What does that mean? That means that what we had as a partial of pressure with respect to x is now equivalent to a defined derivative, definite derivative dp dx. So instead of a partial of p with respect to x inside the boundary layer, we're going to say that's the same thing as our pressure outside, right? So there's some pressure here, P1, looking over at some other point, P2. What do we know about those two values? Well, if flow is going this direction, P1 must be bigger than P2. That's what's driving that flow. So we're going to say that we have that same pressure difference inside our boundary layer, even though there's some of these other complicated things going on inside of that. What else can we do? Well, so we think about some of our conservation rules that we've applied in the past. We're going to apply our conservation of mass. Right? So what we have flowing in and flowing in on in the x direction and in the y direction, that's to add up to 0, right? The mass has to be conserved. There's nothing being generated or thrown out or whatever. The net inflow in the x direction and the net inflow in the y direction have to add up to be 0. Also, if we look at momentums, now we get a little more crazy here. What's going on with this guy? Well, this one might look a little scary at first. Let's break it down, though, in a few terms. So we've got u times du dx. What does that mean? Well, this is our u velocity, right? Oh, our u velocity. It's our x velocity in that direction. And we're also going to get times our gradient in that direction. Here's our y velocity times our gradient of our u in the y direction. This is our momentum part of this. And then inside of this, what is this guy? This is a pressure gradient. And then here we have our viscous shear force, right? So we had the second of u with respect to y times this kinematic, so it's really a new kinematic viscosity. So this is viscous shear force. Alright, so that's the parts of our momentum equation. Oh, and now maybe I should get rid of those guys. See if I can erase those. Just a minute. Let's get rid of those guys. My notes here. So we had our viscous shear force, we had our momentum, we had our pressure gradient. So inside of here, now we have our energy equation. So this is thermal energy coming in with x velocity. Here's a thermal energy coming in with y velocity. We have here, we have the second temperature with respect to y. This is through conduction, y direction conduction. And then last we get some viscous dissipation. Which just means that our fluid has some friction in it, so this is that kinematic viscosity again over its specific heat, and we're going to have some heating that happens from the flow. Usually we can neglect that term. We'll include it here just for fun. As we look back, if we look back at the full development of this in Appendix E, we see that we got thrown out a partial of v with respect to y term. Those gradients are much smaller than those y velocity gradients, so this one is neglected in our analysis here. So looking at those equations that we looked at, so back for a second, these guys, right, our continuity equation, this one here, our momentum equation, and our energy equation. What do we see? We See that continuity doesn't have any temperature or energy equations in it. It's just du dx du dy is 0. Momentum, same thing, no temperatures in there. So those are uncoupled or decoupled from the energy equations. We can solve those directly. So that's good news. It makes it a little easier. We can choose which order we want to do those. We can solve continuity first, solve momentum first. They kind of relate to each other, but they don't relate back to temperature. And then as we look at the energy equation, we saw a bunch of velocity stuff in there, right? We had that u dt dx, we had v dt dy, we had dt dy squared, and then we had du dy squared, right? That was to the second over here. I didn't write those as partials, but all of those guys depend on our velocity field. So we need to solve that velocity first before we can solve the temperature field. Now a little note on compressible versus incompressible flow. Compressible flow just means that our density can change with pressure variation. Not talking about temperature. If we look at the tables, we see that temperature variation causes density variation. This would be only due to pressure. Almost all liquids we can call it incompressible. They're not going to change density. You can push on them a huge amount. Doesn't squeeze more mass into that volume. Gases, on the other hand, we can compress those a little bit, right? We call it incompressible if we're below 30% of the Mach number. Mach number is the speed of sound at those conditions with that fluid. For air, kind of a normal temperature, 300 Kelvin, 1 atmosphere, our Mach number is about 100 meters per second, or the 0.3 of Mach number is about 100 meters per second, or 220 miles per hour. So below that, we can say it's incompressible. If we get above that, we've got some crazy things going on. It gets more complicated, and that will also impact our heat transfer, let alone our flow. Our course, we're going to stick with incompressible flow, even for gases. So it's going to be low speed. We're not going to be at 220 miles per hour or more. We're not analyzing race cars or anything like that, NASCAR. So we're sticking with incompressible. It makes the math a lot easier. So summary, we have our flow equations, continuity and momentum. They're decoupled from the energy equation, right? The energy equation is coupled to the flow field. So we need our velocities, we need our velocity gradients to find the temperature at points. So we need to solve that velocity first. Then we go back, and we're going to stick with incompressible flow. So it's, again, our density is independent of pressure for that condition. Or I should say pressure variation. So if we had some compressed air that was flowing, and we'd have higher density as a result of that. But within the flow itself, we wouldn't have significant density differences due to variations in that pressure. All right, stay tuned. We'll have another lecture coming shortly in talking about 6.5 and 6.6, some similarity parameters and some other dimensionless numbers. So some exciting stuff. This is just a little bridge between flow and temperature.